Alright, here's the construction, number 15. You know what? I did this in class and it kind of went off the page, so I'm going to move this over here so I have more room. Okay, construct the line parallel to the given line that passes through point P. So here is kind of what we're looking for. We're looking for something kind of in this direction. I think it's a good idea to estimate before you do this. We're going to need our tools, we're going to need our compass and straight edge. Alright, first step is to make a random sort of transversal that goes through the point, connecting the point to the line. So let me do that. Okay, and make sure you draw enough line out here. I kind of missed my point, or missed the center of my point a bit. Alright, so then the idea is this angle here we've just created, we're going to copy the corresponding angle up in this area, so that once we make the other side of that angle here that's the same as that one down there, this arm of the angle here will be parallel to this one down here because corresponding angles are congruent. Alright, copying angle, we've done that before. You make an arc down there to span the angle, so we've kind of completed this little slice of pizza here. We do the same thing from this point. Make sure it's long enough to cover the zone you think is going to be parallel. Then we have to measure the span of that pizza slice from here to here. Is that about the right size? That's a little too big. Out there. You can draw this if you want, you don't have to, but I kind of like to see that's what you're doing. Then stab up here and show the same thing. Great. And then there we have it. How come I can't move my my ruler? Okay, and then positioning a real ruler is faster than trying to move this electronic one around, but it's something like this. I just connect these dots now. Yeah, it's about as good as I could probably get it. Let's go ahead and move that down just a little bit and draw the line. Okay, so there's the parallel line. I always like to do this. I always like to show you, yeah, in fact, the answer is this thing here. That's the actual answer. Okay, and that ought to be parallel. Alright, the proof. Let me get rid of the tools here. Okay. Alright, what I should have said at the beginning of this one is we're talking about completing the proof of the right triangle complementary corollary. If I don't say that, then this is a really silly proof. The right triangle complementary corollary is what's being asked to prove here. If you use that as a reason, you can do this step in one. You can do this proof in one step. So forget about that for a second, and let's try to do this. Okay, D is the right angle. That's given from the fact that it's a right angle. How come it's 90 degrees? I think people are forgetting to look kind of down these proofs sometimes and go, oh yeah, this follows directly as this, or this comes from the fact that I knew this already. Right angle, 90 degrees. I'm talking about angle D in both of these. Yeah, this is simply, well, because it's a right angle. Because it's a right angle, that's why it's 90 degrees. When you say because it's in proof land, that means you mean definition of. Okay. I guess I could have typed these. It would have been a little faster. And it would have looked better. Okay. In fact, I think I'm going to do it. Alright, how come D plus E plus F is 180? Well, that one does not come right from here. It's not just because D is 90, then this automatically happens because of anything that happened up there. This one I got to look up at the picture. If I look up at the picture, how come D plus E plus F is 180? Well, it looks like they're all involved in the same triangle. Now this is probably faster. Which we call the Triangle Sum Theorem. Very popular this time of year. Okay. Then, D plus E plus F is 180. How come 90 plus E plus F is 180? Oh, wait. All they did was change the D to the 90. How can I swap out D and 90? Oh, look. I already knew D was 90. That's substitution. My handwriting is actually really better than this. It's just these electronic things. They're funny. Okay. Don't follow me really fast. Alright. Then, how do I know E plus F is 90? Let's get some of this junk out of the way. How do I know E plus F is 90? Well, look up here. I just had E plus F in a sentence up there. Now I have E plus F again here. What's the only difference here? Well, here I had E plus F plus 90, and that equals 180. So basically all that happened here was that I subtracted 90 on both sides. So I need to justify the reason that says, how come I can just subtract 90 on both sides? And that's the subtraction property of equality. Sorry, I've made my window too small again. I gotta scroll down here for you, or up, whatever the case may be. How do I know E and F are supplementary? Well, or sorry, complementary. Look up here. How does this imply this, or what is it about this previous business that tells me that they're complementary? Now, some people are looking back in the picture all the time and going, "Oh, E and F are complementary because of that thing, or because of some other crazy reason." Well, the last step in the proof, of course, has to have something to do with the stuff that came before it. Well, look right here. E plus F is 90. Why are they complementary? Well, that's what complementary means. Complementary means that they add up to 90. So this thing deserves the term complementary because we have satisfied the definition of complementary. Okay, so we used two definitions in this one. It was here. It was I met the requirements of the term, so I was able to apply the definition. So it earned the term complementary because it met the definition. Here, I was given a term. D is a right angle, so then I got to sort of bleed the truth out of that definition. The fact that it's right angle means, oh yeah, that means that it's 90 degrees. Definitions kind of work as biconditionals that way. All right, let's go back up there so you can see all that. All right, use the diagram on the right to answer the following questions. Name the largest scalene triangle. Okay, well, we've got some different categories of triangles in here. There's a big isosceles here. Here's a big equilateral. Here's an isosceles. Here's a scalene, but it's not very big. Of course, I've got bigger overlapping things like CFA. CFA is one of the biggest triangles in the whole shoot and match. In fact, I think it is the biggest triangle in the whole shoot and match. And it's 10, 5, 5 squared 3. That is scalene, so we got it. CFA. Equilateral, I found one before, it was 555. Right, and then name an obtuse isosceles. Obtuse isosceles, I saw one of those over here. We need a triangle that has two sides that are the same, but also has to have a huge angle bigger than 90, so that would be ABF. Name an exterior angle of that triangle, ABF. The only one I see here, exterior angles are when you take a triangle and you extend one of the sides. I see one right here. If I took this triangle and it looks like that one's already been extended, the angle I want to name there, I'll call that angle CBF. I can't just say angle B, it would be ambiguous. Alright, 22. These are parallel. Find x and y. Alright, if these are parallel, I've got some same side interior going on here. Wow, that's really big. All this stuff together is same side interior with this y here. That makes that sort of turnaround U-turn C-shape thing. So, gosh, what is all that together? That whole angle is 50 plus 30. That's 105. So, same side interior doesn't say, you don't have to say y. But because parallel implies same side interior, I know that y is 75. Okay. Then to get x, you could probably mess around with this triangle or this big triangle. Actually, this big triangle is not too bad. ADC, because I know that this thing is 55, and I just found that. But also, look, I've got AIA right here. I'll do 3 here. X and 50 are AIA angles. Okay. Just so you can see that later. Whoops, that's an A. Great. Okay, using the diagram at the right, these are parallel. Oh yeah, this is the silly one where we didn't even need to know that. The segment AB has nothing to do with any of the questions here. I think maybe it was taken off of a bigger problem or something, but I can find x and y without knowing anything about this stuff up here at AB. Although I could use it. I mean, I could use this 60 here, and I could find this angle at B is 60, and I might do an exterior here with the 130 and the A and stuff. But you really don't need to. I'll use exterior angle theorem first to say that 130 is the same as 60 plus x. What did I just say? 130 equals 60 plus x. That tells me x is 70. Well, if x is 70, y is easy. Y is linear pair with that, so there you go. Nothing to do with the parallel AB. Find the measure of one interior angle of a regular polygon with 18 sides. Oh my gosh. Alright, well, the way I've been saying to do this in class is let's talk about exterior. Got 18 sides in this thing, so I don't want to draw the whole thing, but it's got 18 of these exterior angles. The exterior angles all add up to 360. 360 by 18 is 20. Now remember, that's the exterior angle. So the interior angle is the one I care about. Well, if that part's 20, this part has to be 160 because it'd be supplementary. Find the sum of the measures of the angles of an octagon. I think for that one you pretty much have to use the formula. It doesn't tell us it's regular. It's kind of a pain. You could think of it as regular and then try to find one measure and multiply by 8. That's just kind of silly. Whatever 6 times 180 is, handy dandy calculator, it's 1080. And there we go. There's only a couple left here. I think I'll make it in my time. Find the sum of the measures of exterior angles, one at each vertex of a convex decagon. Don't think too much about that. Once we stopped right here, whoosh, we know it's 360. Who cares about that stuff? Although convex is kind of nice. Alright, the measure of one interior angle of a regular polygon is 150. Well, if it's regular, they're all the same. I'm going to do this thing again where I kind of draw part of it and then don't draw it all. It tells me this part's 150. So if that's 150, the exterior is 30. Again, I just like dealing with exteriors. You could do this with the interior formulas. It just takes a while. That is, because there's a bunch of these 30s, and they go all the way around, and they're all equal, and there's a number of them, and they add up to 360. So if I simply take 360 divided by 30, I'll find out how many there are, and there are 12. So, done. Regular polygon has exterior angles congruent to its interior. Oh my gosh. Well, the exteriors and the interiors have to be supplementary. So I've got supplementary angles here that are congruent. Guess what size they are? They've got to be 90. How many sides does the polygon have? We're talking about something that has 90-degree angles in it. Don't think too hard about that. If you've got right angles in it, you must be a square or a rectangle, but if it's regular, it's got to be a square. But the question is, how many sides does it have? So that would be 4. Alright, we got all kinds of parallels here. I did this one in class, in most classes. Great, find x, y, and z. Well, couple of things. 84 is congruent to lots of stuff. 84 is AIA with 4x on parallels A and B, and it's corresponding to z on these, actually on the, sorry, wrong parallels. 84 and z are AIA on the C and D, and 84 and z are corresponding on the A and B. 84 then equals z. 84 also equals 4x, so x is 21. Now the fact that x is 21 tells me that this angle in here has to be 42, which is a nice piece of information. I could say 42 is corresponding with this little angle over here, and I could figure out what that is. I could also go, because I'm trying to figure out the 3y. 42 plus 84 plus 3y would have to be 180 in here. Or I could look at this triangle. I think more people see this triangle and go, okay, if that's 42, this angle in here is 84 because it's AIA with that, or it's vertical to z. So I have a triangle. Any way you do this, the calculation's going to look like this. 84 plus 42 plus 3y is 180. So this is 126. That's a 3y. And so 3y is 54. Divide both sides by 3, I get 18. Alright, according to this theorem, sum of the interior angles of polygons is 180 n minus 2. How do you figure that out? Well, we did this in class. In general, you take any polygon of any number of sides. I'll do 5 and 6 here so you can sort of believe me. Those are not really good pictures. Pick any vertex and draw all the diagonals you can from that vertex. You're going to chop the thing up into these triangles that don't overlap. That's a really bad one. And the angles of those triangles will add up to all the angles of the polygon. How many triangles do you get? Well, if n equals 5, this is the number of sides, guess how many triangles we get? 3. Here n was 6. Turns out I'm going to get 4 triangles. No matter what, I get n minus 2 of those triangles every time. And each one of those triangles is 180 degrees. So that's where we get it. We get n minus 2 of them, and each one contributes 180 degrees. Alright, that's it for the review videos. I will see you at the test. Good luck.